Hi there. For this next video, we are going to be continuing our discussion of variables and talking about how are variables stored. And so what we want to talk about is binary data. You know, hopefully from SY110 Cyber 1 that everything inside your computer is really just bits and bytes. So just a reminder, a bit is a 0 or 1. A single, and that's what is physically represented by like a low or a high electrical charge inside a classic computer. And a byte is just a group of bits, 8 bits. And kind of for historical reasons, a byte is the smallest unit of numbers of bits that we can kind of access at one time inside our CPU. And then how do we actually represent numbers or things with bits and bytes? So for numbers, what we do is use base 2. So let's think of a normal number like 27. Okay? What does that actually mean when we write 27? It's powers of 10. So this is 2 times 10 to the first power plus 7 times 10 to the 0 power. And if it had more digits, it would be those digits times higher powers of 10. And that's why all the digits in a regular number are always less than 10. They only go up to 9 because we're talking about base 10 in normal numbers. But if we want to write this as a binary number, then we have to think about what powers of 2 come out of it. So 16 is the largest power of 2 here. That's 2 to the 4. And if we imagine subtracting 16 from 27, we would have 11 left. So that leaves room to take out an 8, which is 2 cubed. And then if we took the 8 out of 11, we would have 3 left. So there's no 2 squared, but there is a 2 to the 1 and a 2 to the 0. Right? So this is 16 plus 8 plus 2 plus 1. And you can check that that equals 27. And then according to the powers here, so there's kind of a 0 times 2 squared. And so we would write this in binary as 11011 base 2. You will get a lot more practice of dealing with binary data and base 2 stuff in your computer architecture class, so we don't need to go too much into it now, but just to say that any number, if we have enough bits, then we can represent that number in bits. And for example, the int data type uses 32 bits. And that means that we can actually represent any number from minus 2 to the 31 up to 2 to the 31 minus 1 with an int. And that's up to the billions in the positive and negative range, which is usually at what we need. And if you wanted something bigger, you can see in the notes there's some discussion of slightly other different types. There's a long int type, and there's even a long int, which is sometimes the same as long int, and depending on your computer, you may even have a 128-bit integer types. Okay, so that's generally how binary data works, and we know that everything has to be represented in binary sooner or later. What about the specific types that we are going to be using in C? Well, we remember that there's only actually 5 types that we're going to be dealing with in C. So let's think about each one of them in turn. So we just talked about ints. So an int is going to be 32 bits, which is 4 bytes. Remember, a byte is just 8 bits. A double is the other kind of number. Remember, doubles can be like fractional numbers. And they're called doubles because they're twice as long as an int. So those are going to be 64 bits, and that means a total of 8 bytes. Don't take me too literally. Actually, there's a slightly other reason why they're called doubles. But anyway, yes. And I should also say that this applies on any modern computer. With some very old architectures and potentially some other computers in the future, these would use a slightly different number of bits for each of these types in C. But this is going to be what it is for anything that we're dealing with in this class. So we also have bool. And bool is an interesting one. We only really need 1 bit for bool because it's 1 or 0. That's exactly what bool is. But remember we said the smallest unit of memory that we get to access at a time is a byte. So it's actually going to use still 8 bits, even though there's only one of those bits that it really cares about. It's always going to be 0 or 1, but it's going to use 8 bits to represent that. Then a char, a single character, is an ASCII character, so those also use 8 bits, but you actually use at least 7 or 8 of those bits, so that's also 1 byte. And finally, a string. Remember that a C string is not built in to the C language, and so it depends on how it's defined. So I'm going to put some question marks, we'll actually see how it works, a little bit hint of how it works, and we'll learn in more detail how that works later. So this is what we see as kind of the size of representing all these things. Let's look at an example, because I like to have examples. So I wrote this program called showbin.c, so you don't have to just take my word for it. There's a bit of magic here. This is what's called a function definition. We haven't learned about this at all yet, but this is going to print the binary representation of anything that we want. And then down here, this should look kind of regular then, because I wrote that cool function up top and a macro. So it's going to ask us for an int, a double, a bool, a char, and a string, and then show each of those in binary. So let's compile this. Showbin.c is our source, and showbin is our output. It works. The compilation worked. So let's run it. And for an int, we can do 27. And what we see is, and there's a subtle point about this in the notes as well, because this is what's called a little endian computer system. This is actually the lowest byte of that int. And this is the 11011 that we just worked out on the board there. So if I write the same exact number as a double, you'll actually see the same thing, 11011, but it's in a different part of the double. And there's also something else down here, because doubles, remember, can represent floating point numbers. They're stored in kind of a binary scientific notation representation, if that makes sense. And if it doesn't make sense, don't worry too much. You'll learn more about it in your computer architecture class. So remember, when we input bools, we still input them as numbers, not as the words true and false. So let's try 1. And you see that it's all zeros, but just 1. So it's only using 1 byte to represent that. And a char, if I have, let's say, a capital C, that comes out like that. And now a string is a little bit interesting. When we input a string, and I see that I misspelled interesting, but I'm not going to change it. What happens is we get a whole bunch of bytes inside that string. And you may have guessed this already, but a string is actually represented as a string or a sequence of chars. And for us, the C string type is always the same number of chars, no matter how long the string is that we typed in. And what I want to point out is that you see this representation of the letter C. You'll notice that that shows up in our string once we get past these initial letters of interesting. You'll see a bunch of C's right here, because that's where the C's are. And so this actual string only takes up these initial bytes. That's how many letters I typed. And then the rest of it is actually ignored, but it's still part of that type. And so this is giving you a little bit of hint of how the string actually works, which we'll learn more about in a few weeks. Also, one very important hint that you should take is that there's a limited size of strings. And if you typed it too long, some strange stuff might start to happen. Okay, so that's it about binary data.